Hi there, good afternoon everybody. Very excited. Wilhelm Swart here from BluESP in South Africa, sunny South Africa. Yeah, like everybody else in the world, we're also in lockdown, so being at 5, now in 4. From 1st of June, we'll be lockdown 3. But we also just thought that we'll make this lockdown period very, very efficient, very productive. And thus we launched this webinar series, this 9-week webinar series. So the key focus is before and during the lockdown, there was a lot of, and even after, there's already quite a big move to more remote operations. Less eyes, less ears on site. The environment is very volatile and uncertain and ambiguous at times. Clients are looking for more agility in their projects, fast turnarounds, or paybacks, like 3 to 6 month paybacks in a digital transformation project, or really, otherwise don't do it. More focus on data analysis, more cloud, more embedded AI is the norm of the day right now. Much more collaboration between various vendors, various business partners, also with the end users and with the various parties at stake. So yeah, I think it's a very important time that we should all, prepare ourselves. So, we at BluESP, but we also use this webinar series to help our clients to upskill and cross-skill and to learn about, using these intelligent, agile technologies that we are going to talk about today and that we bring to you in this webinar series. So there's a continuous focus, as the AspenTech CEO talks about, that we need to run operational assets safer, greener, faster and longer in the spirit, and that's what we're focusing on. So as you can see on the screen here, we're bringing 3 key themes to you. So basically, firstly, the APC team, the Advanced Process Control team, will basically start today. They will, this team has just finished commissioning large projects in Canada, busy with projects migrations in South Africa, various benefit studies in South Africa. So really know their stuff and has been around and done lots of APC work for the last 15, 16 years of BluESP. So we'll talk a lot about that. You can also see there's also, for each one of these sessions, we have 2 or 3 basically topics. So the next one up is asset performance management. This team has also just finished large Intel projects, 3 of them with mining companies in South Africa, in Botswana. They just engaged with one in Australia and busy with various multivariate analysis proof of concepts right now, looking after process quality. So they've got a lot to share as well. And then the last themes is manufacturing execution system. So involved with projects in Asia, just kicked off a very large metal accounting project in South Africa, looking in managed services projects related with various large mining companies also in South Africa and in the rest of the world. So if we look at the next slide, Kevin. So really what we wanted to try and do here is use the slide to just introduce to you the intelligent technologies that we have in 4Sight. So really what we believe at 4Sight is if you take data and intelligent technologies, you get what we call an intelligent enterprise, or Enterprise 5.0, and that's what we're focusing on. So if you look at this, it's a combination of data, technology and people, and using those and bringing them together to bring new business models to the clients, and most of these things today is happening in the cloud. So these intelligent technologies that we talk about is things like IIoT, so Industrial Internet of Things, or artificial intelligence, machine learning, deep learning, adding that to existing software sets that's been around for 10 years, for 15 years, is the norm of the day. That's what AspenTech focus a lot on right now. Advanced analytics is also a lot of that type of work is being brought into the software, enabled by the software. Multivariate analysis to basically go through complex data sets. Simulation, planning and scheduling is quite core in there. Improving the user experience with virtual reality and augmented reality tools. And also all this information needs to feed up into the ERP, the SAP environments. So that linking is very important. So those are some of the intelligent technologies that we depict on the screen. These technologies are brought to you by really three key subsidiaries in 4Sight Group. So the first one is the asset automation subsidiary, APC Technology, and they focus on very much measuring the data, connecting to the data, controlling and making it safety, doing visualization systems. They are multi-vendor, so they work with the likes of ABB, Siemens, Schneider in automation projects, and we work very, very close with them. In the middle, and really is BluESP. So BluESP, as an AspenTech reseller and as a integration solution provider, is very much focused on transforming data into information, bringing wisdom and knowledge and intelligence to the data. And then the third party is simulation engineering technologies, a bunch of 25 simulation industrial engineers, also in Johannesburg, very much focused on simulation of, constrained simulation of mining processes and industrial processes, and also quite a lot of deep skills in planning and scheduling and simulation of that. So really, those are the key subsidiaries that bring these technologies to you. So if we look now more detailed at BluESP on the next slide, please. So, the way that we see BluESP is really an agile and dynamic company. We basically use AspenTech as our road models to learn from them, to learn, they've got like more than 2,500 engineers. They've been around for 37 years, and they develop some of the best asset optimization technologies out there today. And we learn from them and we bring it to the local market. So, some of these technologies, is things like advanced embedded AI in their software. So more and more they take existing software that's been proven and tested, and they bring AI and machine learning to it, into the likes of advanced process control. We'll see it during the course of these webinar series, or, hybrid models and machine learning. Like example of that is the GTOC technology, where they use these technologies to orchestrate much bigger plant areas. Kevin might talk today about dynamic advanced control models and self-learning models that, that your plants and your control models don't auto-tune itself and don't go out of sync, or, things like artificial intelligence powered cognitive guidance systems to make, the work experience much better. So various different things. So if we look at, the way that AspenTech positions their products. So the first set is the design sets of software, which you can see at the bottom there. So all about, how do I simulate a new process? How do I design it? How do I cost it to its optimum? And how do I build it? Because if I'm going to build a new plant today, I want to build the best possible that I can do. We're not focusing too much on the design tools in this webinar, but there's a set of that. The next one is, how do I maintain and run my operational assets better? And so there's a whole set of tools, for example, related to predicting and preventing asset failures, the Intel technologies, which will come later in this webinar series. Also things like predicting and preventing process quality failures, and also simulation of maintenance and risk environments. So quite a lot of tool sets there in this asset performance suite. On the right-hand side, that basically adds wisdom, knowledge, and intelligence to data. In the area we're going to focus today is very much in the operational technology. So how do we run the plant better? We start by linking, aggregating the data, growing the data, and basically, transforming that data into information with historian type systems. And then, next one is we would, for example, visualize that data in operational management and reporting system, MES systems, so do mass balancing or doing metal accounting solutions or enterprise reporting. And then another key part is obviously advanced process control. So key focus is optimizing control of the modern day operation. So, that's the theme of today. And with no further ado, I'm going to ask Merinda Westcott, which is the business unit leader of our advanced process control division at BluESP, to just tell us a little bit about herself, and also to introduce the speaker of today. Merinda, over to you.
Thank you, Willem, for that introduction. Good afternoon, everyone, and thank you so much for taking the time to attend this webinar. As Willem mentioned, I'm the APC business lead for APC at BluESP. I've been involved in advanced process control for about 10 years. Before joining BluESP, I was with SGS's Advanced Systems Group, where I did APC projects on mining sites, mainly in Africa, Australia, and Canada. Before that, I worked for Impala Platinum for 12 years in various roles, including process control, project management, and plant process engineering. So today it's my great pleasure to introduce our speaker, Dr. Kevin Brooks. Kevin has a BSc and PhD degree in chemical engineering from the University of Wits, Witwatersrand. He has over 30 years experience in advanced process control, spanning many applications in both petrochemical and the mining industries. He joined BluESP in 2007, where he was an instrumental member of a team that introduced model predictive control into the mining industry. His most recent project was a year-long engagement with Vale in Canada. Kevin is also very actively involved in the South African Council for Automation and Control. He was the president of this organization in 2013 and 2014. Most recently, 2019, he was appointed as a visiting adjunct professor at Wits, where he's currently assisting with the teaching of process control. The title of Kevin's presentation today is Advanced Process Control for M, Control and Optimize Using Models and Data. With that, I'd like to thank Kevin for sharing his extensive knowledge and experience with us today. And over to you, Kevin. Thanks.
Thank you, Merinda. Thanks for the kind introduction. And thank you, everybody, for taking some time out to attend. We've been very pleased with the attendance we've got. So today I want to talk about APC in M. I guess I need to define what M is. It's metals, mining, and minerals, or in some different order. And I'm just going to say M. And really what I want to talk about is how APC has become part and has not become part of this world. So just to give you a bit of agenda for today, I'll introduce the subject, and I'll define some jargon because I think it can be confusing when we talk about APC, MPC, MVC, and many other things. I'm going to talk about MPC in the petrochem industry, not because most of you are in petrochem, but I want to share its success there, and then move on to its use in the M industries. I'm going to look at a case study to make the examples concrete. Towards the end, I'll give you some pitfalls that you can fall into doing these projects and some conclusions. And there should be plenty of time for a question and answer session at the end. So as an introduction, I doubt whether anyone here is old enough to remember the analog panels that we used to use to control plants, but those are them on the left. Lots of dials, lots of strip charts with pens drawing on paper, and red lights at the top, often which were alarms. And these control panels were analog. They used pneumatics, airflow to do PID loops and all sorts of clever stuff. But that limited what we could do from a control perspective. The introduction of the digital control in the mid-70s really led to the kind of control room we're all used to now. Lots of screens, lots of computers, and less dials and strip charts. But from our point of view, what they really allow is for the use of powerful control algorithms. So if you've got computer programs running your control, you can do more sophisticated calculations. Advanced process control isn't one technology, it's a set of technologies, and people have different definitions of what they might be. I've picked out 3 or 4 here to talk about or to mention. And the first is what used to be called intermediate regulatory control, or it's now sometimes called ARC, advanced regulatory control. And typically these are schemes that you can build in your DCS or PLC system. They give you advanced functions like ratio control, a split range control where you do different things depending on whether you're above or below set point overrides where you normally control like that, but sometimes control in a different way, constraint control, and decoupling control, which is kind of a first attempt to deal with multivariable systems. I've just drawn one here, which is a advanced regulatory control on a boiler. We've got a master pressure controller here, which is writing down to various elements, and there's a linearizer there. And so this has become quite standard, for instance, for boiler control. And this would be an example of ARC. The problem with some ARCs, or even most ARCs, is that they are very well understood by the person who wrote them originally, and when that person leaves the company, no one knows how they work anymore. So they have a maintainability issue. Three other technologies include expert control, fuzzy control, and MPC. So expert or rule-based systems are computer systems that emulate the decision-making ability of a human expert. So if you have an expert who knows how to run your plant, why not just copy what they do in a computer program? That's what an expert or rule-based system does. And these are quite popular for some classes of control. Of course, one has to ask, why would we limit ourselves only to doing as well as a person can do? Maybe we can do better. Fuzzy logic is also popular, described by if-then rules, and with inputs that can be cold or very cold. So the inputs can be fuzzy. I've done a drawing here of a fuzzy system. Became very popular in the mining space at a time. I think, and they certainly can do a job. I think when we come to optimization, we find that these systems have limitations in terms of building the rules we would need to optimize the system. And then there's model predictive control, which is really what we're going to talk about today, which uses a dynamic model to predict where the process is going and then potentially changes the trajectory of the process in a way that is optimal and therefore makes money. So if we're going to do model predictive control, we need models, and we can classify these models that we use as linear or nonlinear, empirical or rigorous. So starting with empirical models, by that we mean that we find the models using data. We do a plant test, or we go through historical data and we calculate some sort of statistical model. So there's no physics behind this, it's all statistics, if you like. So this picture here is of what's called a step response, which is the response of one variable to a change in another over time. You can see that's fitted. So it's not fitted very well over there, but this is a fit of data, and we could express it in this difference equation form. This is the so-called FIR form. So these models are empirical. They have no background in the mass, energy, and momentum balances that chemical engineers are so fond of. So we could derive rigorous models for our processes, and we do. These are accurate. They can extrapolate. They can take us from one point to another, but they turn out to be expensive to build and validate. And in fact, to validate them, we often need the data that we need to derive the empirical models. And here's a little example of two equations for the volume and mass of a material in a flotation cell. So we might start out writing equations like that. So what we find in practice is that the large majority of commercial MPC applications use linear empirical models. And that's from a cost saving perspective. A little bit of history about these MPCs. Originally, they came out of the oil refining world. Mid-80s or early 80s, Cutler, who invented a formulation, if you like, of MPC called DMC, Dynamic Matrix Control, which eventually became DMC Plus and DMC3 from AspenTech. Unfortunately, Charlie Cutler died a couple of months ago, I've been told. Round about the same time, some people from Honeywell and some companies that Honeywell acquired created a project called RMPCT, Robust Model Predictive Control Technology, over here. And a different group at Shell, led by Pascal Marquis, developed a product called SMOC. I believe that stands for Shell Multivariable Optimizing Controller. Okay. And that's used a lot in Shell refineries, even currently. So it was an idea whose time had come. In 2003, Joe Chin and Thomas Badgewell did a survey with the companies of MPC applications, and they list 3,000 odd applications in refining, petrochemicals and chemicals, and more than half of those used AspenTech technology. So this is clearly a successful technology. If there are 3,000 applications, and that was 2003, you can probably count on that being doubled by now. In the oil refining game, nowadays, if you're going to build an oil refinery, you would specify the MPC as part of the deliverables of the EPC. However, the 2003 survey by Chin and Badgewell only lists 37 applications in mining. So if we compare that to the amount of applications in petrochem, it's very small. More recently, Rogers and co-workers looked at the literature for what's been published on MPC. And they list a number of references in a number of processing areas. And they're all very interesting. The trouble is only 6 of them in total are industrial applications. So something's strange, because either we're not doing MPC in M, or we're not talking about it. And I think it's a bit of both. We're not doing as much as we could to improve operations using these technologies. And then the ones we have done, we're not publishing. So there's room for improvement here. And here's a little picture, some of you may recognize, of a grinding mill and how we would at least specify the inputs and outputs for it. So clearly we're not going to do MPC because it's a cool technology and we like building models. We need pointers to what kind of processes would benefit and what are the financial benefits. So because MPC is model-based, it inherently handles the interactions within systems. So a lot of the processes we deal with are interactive. If we increase the feed to a mill, more than one thing changes. We may have to make other changes to compensate for that. So there, the model predictive technology helps greatly. In some cases, we're limited by different constraints at different times. It could be day, night, summer, winter, or product grades. So we may have to change grades. In that case, you want a flexible control system. This third point is really very important. If your system makes more money when it's operating close to constraints, it is a good candidate for MPC. Because what the MPC does is it takes the operating point that we have now, somewhere over here in the middle, within the operator's comfort zones, and pushes towards the operator's discomfort zone, where the operator won't operate. And if in that pushing we make money, then we can make that money consistently. So if we need to track optimization targets, then MPC is a good technology. If we need to move to new targets, this perhaps is less important in M, but maybe if you're running a polymer plant, it's very important. If you have unusual dynamics, and if you can measure and model the disturbances. So this we do see in M. We can measure grades coming into a mill or a flotation plant, and we can get models for how those affect that plant. And in that case, we can do some very powerful proactive control of the system. So despite the paper by Rogers, I thought I'd put together a list of where I know MPC has been done in M, either where we've done it or where colleagues have done it, or I've just heard about it. And it is a large list. Mills in particular, primary, secondary, ag, sag, isomills, crushers, flotation, which I'm going to talk about later, leaching, some work I've been doing recently, and some work I know that was done at Alcoa. Thickeners and clarifiers have been done. We've done cyclone banks. There has been some look at dense media separation, not as much as I would like. We've done electrowinning. Boilers are interesting because you shouldn't ignore the utilities on your plant. This might be low-hanging fruit for quick wins on benefits. Flash dryers, acid plants, jig plants, hot gas generators, and ones that I don't know so much about, but which I think will come, are smelters, solvent extraction. And although it may seem like a simple unit operation, it looks to me like there are cases where filters could benefit from this technology. So this is a wide range of unit operations that we have and could look at with MPC. So for a case study, we're going to look at work done by this group in Mount Isa. Mount Isa is in Queensland, Australia. It's a very interesting site geologically because it has a vein which is lead and zinc, and another vein which is copper. And so there are two processing plants on one site doing two different processes or making two different materials. It's very famous for its very tall stack because there's a lead smelter on site. And so they put the effluents up high. The work I'm going to talk about, there are some publications. Myself and Ryan Courts have written a paper, and Adam Price, who is with Glencore, and some of his colleagues and me wrote another paper which is available. And we did a number of projects on flotation, both zinc and lead circuits. And I'm just going to take as an example of what we did 2 cells. Obviously, we had more than 2 cells, but just to make it easier to understand. So we're going to look at how we would model 2 cells. And in our particular sort of model example, which is very much like the real example, the concentrate and the tails, their grades are measured online. In this particular application, they're measured by XRF. And we're going to show how we develop linear dynamic models from step testing. To understand the system, we need to know what are the inputs and the outputs. And for this particular system, the airflow to the two cells are inputs. We can independently change those, as are the reagents. Over here, we can independently change those. And the level, there's only one level between the two cells, and we can change that with the dart valve. The things we are controlling are the profiles, for instance, the difference in air, the dosages of the reagents, and obviously the concentrate and tail grades. What are our disturbances? What are the things that we would, where if there is a change, we would like to reject that change? Well, those are all over here on the feed side. So that's the feed rate, feed density, and the feed compositions, which are also measured. Okay. So how do we do this? Well, what we do is we go off and do a series of step tests. Okay. And what I've shown here is a period of intensive step testing of the air and the level and the copper sulfate, which, if I remember correctly, is the collector, and the X, which is the sodium ethyl xanthate, which is the depressant. I may have those two the wrong way around. And over this period here, you can see we are injecting steps into those inputs. So we're doing a planned experiment where we're moving this. This in fact was done by the computer. Okay. Historically, we used to do these things manually. We still sometimes do it at the early part of a project, but afterwards we've got tools now that will do it automatically. And I've shown just two outputs here. So these are the primary rougher con zinc moving around, presumably as a result of all these moves we're making here. And the same with the primary rougher tail zinc. Those are moving around. Something went wrong there. We'd have to get rid of that data. And the reason I've shown more data is just to show that some of the data that was not where we weren't stepping these variables can still be used because the operators were presumably moving some stuff around here as well. Okay. So this is the AI plot, if you like. We never used to call it that because we didn't know what AI was, but this is the part where we take this data and we attempt to turn it into models. And the models look like this. These are called unit step responses. The unit refers to the fact that they are drawn for a step of one in the input. So for instance, this model here is the response of the concentrate zinc to a change of 1, presumably %, in the level, and with over a 90-minute time period. So what do we see happens? Well, nothing happens for 10 minutes. There's a delay, and then there's a reasonably sharp drop, and then the zinc stays reasonably constant. Some other models down here where the density goes up, and this causes the tail zinc to go up. So these are statistical models, they're fits. And the more data we have, the better the fit. And we've got very sophisticated tools now for doing this fitting in the AspenTech suite of software. So what can we do with these? Well, we have to define our control objectives. So for this process, we want all grades within limits. We want reagent dosages within limits. Ideally, the system should find the reagent dosages. But generally, the metallurgists do want to say, well, even if you want to reduce the dosage below 0.1, I'm not going to let that happen. So we have to keep dosages within limits. And then we like to maintain a particular air and level profile down the bank. And then for optimization, we maximize recovery by maximizing airflow, and at the same time we minimize reagent dosing to save money on chemicals. What do the results look like? Well, these are some results from the paper by Brooks and Courts. And what we're drawing here are histograms of the dosages of the two chemicals. And the dotted line is a histogram, a frequency distribution before we did the APC, MPC, and the solid is after. And you can see very clearly here that we have a sharper distribution, which means we're controlling better, and we've moved the average significantly down. In this case, from 7.8 to 6.1. That's a 20% improvement. That translates straight into the bottom line. Similarly with the ethyl xanthate, it's even more, 38%. So the aims of the project were very well met, and this is subject to always being within grade constraints and recovery constraints. So this is a very visual way of looking at the results from these sorts of projects. Here's just an example of what might happen when you switch an MPC on in the evening. So these are just time plots with the dotted line being now, and everything to the right of the dotted line is a future prediction. There's always taken by the fact that, in fact, an MPC is really the only place in a plant where you can visually see at least some idea of what's going to happen in the future. So this is about a couple of hours into the future here. So at this point here, we switched on the MPC. It picked up the air. It lowered the ethyl xanthate here and here, and the copper sulfate. These are the disturbances which we've left constant in this simulation. And the result is the Rafa conc came down, but it didn't come down below its low limit. Rafa tails came down a bit, which is recovery, and then the dosages came down. So this is a simulation, but it does show how you can make money using coordinated moves while maintaining within the constraints of the system. Okay, I did say I'd mentioned some pitfalls. The first one is I've seen MPCs used and other control systems used to solve very point problems, very small scope problems. I would say don't do that. Have decent scope on your controllers, because then they will show real economic benefits. Do a plant-wide techno-economic study. This is something we have pushed for and have done for a number of clients, and we use them to identify applications with a 6-month or better return on investment, which is great, to have a phased rollout. And this means that the program becomes self-funding, because the first project will pay for the subsequent projects. And you may have to pay for this study, but it's worth it. And then have a technical champion on site, or nowadays, as we've learned, I think in the last months or so, we can work remotely with the right connectivity. But have someone from your company, your operation, fully involved. Can be a metallurgist, a control engineer. This person monitors the applications and gives first-line support when project is over. You may want to keep the consultants to give some backup, but this is a very important role. Shouldn't be a part-time role of a DCS engineer somewhere. That doesn't work well. Change management is very important in these projects, as in most software projects. So I'm sure you know this, but have a good project sponsor that aligns the operation behind the new technology. Beware of my colleagues who think steady state only. The process is dynamic. That's why you need a control system. And the more dynamic it is, the better the control system you need. And do thorough training of the operators. MPC is great because it is a model of the process. So inherently, you've got a simulator. So you can use the simulator for training. And in the future, I'm sure that gamification will be used to improve these trainings and to make sure the operators make the best use of the tools. So in conclusion, MPC technology gives you this opportunity to optimize in real time, minute by minute. We run the things, in some cases, even faster than once a minute. And this matrix model, that picture I've shown you, gives you a unified view of the plant that you can use for other studies. An upfront study with a roadmap and purposeful change management will get you there. We've talked about, Willem talked a little bit about AI. I haven't talked about it because I've been looking back rather than forward. But my one forward look is about the large amount of history that you people already have from your plant in your historian. And why aren't we using that to develop models? And there are good reasons. It's difficult. It's hard to trawl through manually. But I am doing some work with a colleague in Germany. We've published a couple of papers. This is the first one where we use sophisticated techniques to slice the data in a way that we can then use it for model identification. So thank you very much. There are the references that I've used during this paper. And without further ado, I'd like to move into the questions and answers. So back to Merinda.
Thank you, Kevin. Thank you for that very insightful presentation. I'm sure everybody found it extremely useful. I've got a question here from somebody who's asking, what would I do if my process is really very nonlinear?
Yeah, and what we found is that there aren't too many very nonlinear processes. So the linear technology has feedback in it. So we develop these models, and while we're running, we are adapting them as we run by putting feedback into them. And provided you do your step testing around the area where you normally run, the linear models manage fine. If you have a real nonlinearity and you know what it is, you can build it into the models in a number of ways. You can use gain scheduling, or you can build a fully nonlinear controller. But I would say that it's less than 5% of applications need that. Another way of looking at it is the 80-20 principle tells you you're going to get 80% of the benefits with the linear controller. You're going to have to spend a lot more money to make the nonlinear controller, and the benefits are probably not going to be that high.
Okay, great, thanks. We've got another question here. You talk about doing studies on the plants. Do you ever recommend that extra instrumentation should be installed for the MPC?
Yes, I mean, that does happen. That during the course of the study, we say, well, we can do some stuff with the instruments you've got, because almost always you can. After all, the plant's being run with that stuff. But that if you put this instrument in, then you will do a lot better. One example that comes to mind, maybe a trivial example, but one that makes a big difference, is oxygen in the flue gas from a boiler. If you can measure that, you can really do optimization of the boiler. So yes, we do that.
Okay. And then, yeah, there's another question that's related to instrumentation. If you have a laboratory value that you only measure once every hour, could you use that in a MPC system?
Yes, you can. This is the field of inferentials or soft sensors that I've not talked about at all here. Maybe I should have, because it's been a big part of the gains that we've had in the system. So effectively what you do then is, if say you've got a lab value that's measured every couple of hours, we use these new powerful statistical techniques, supervised or unsupervised learning, to develop a model that's based on the process inputs that we do have, temperatures, pressures, flows. And then when we get the lab value, we use it to update the model. So it's a model controlling a model, and that works very, very well. It's been very effective all over the place. And as the AI machine learning techniques improve and are easier to use and more robust, these soft sensors are going to become more and more important.
Yes, absolutely. Especially in the mining industry, instrumentation is an issue. There's a question here from Robbie. Can you comment on instrumentation in mining? Is this a limiting factor for MPC in general?
Yeah, it's hard to answer a general question, but yes, I think there are if you come from the oil refining world and then you find yourself doing this kind of work, it is noticeable, not necessarily that the instruments are not as good, but the instruments don't work all the time. So that's something you've got to take into account, that I think because of harsh environments and you know, slurry flows and so on like that, then the instrumentation does become an issue. And then it is an issue with online analysis. I think where we've had our great successes has been where the online analysis has been good, robust. The instruments have been properly maintained and calibrated.
Yes. Okay, I think there's one more question here, a very interesting one, Kevin. How does the MPC fare in processes that involve constraints that cannot be measured live? For example, a process involving biological constraints, which take a few days to measure.
Yeah, those are very tough.
Yes.
So again, you've got to appeal to the inferential world. And then what you say is, I'm going to do the best inferential I can, right? And then I'm going to control conservatively. Because if I know I'm only getting an update on my measurement in 2 days, I'm going to have to stay away from the constraints by a fair amount in order to allow effectively for what is the noise in my measurement, the error in my measurement. And that's a very tough one. I've certainly done applications where the measurements were shiftly, which largely means once every 12 hours. But even then, you've got to be careful that that your inferentials are accurate and that the updates are done. You might, in that case, want to suggest to the plant that the lab frequency be increased to twice a shift, because that would give you a better comfort zone.
Yes. Yes, and then we've got a question here. Do we typically write extensive logic to account for edge cases that might occur? So how do you decide that the controller is too uncertain and should probably avoid taking any action at all? Fall back to the base layer.
Okay, well, I kind of hate doing that, so
Yeah,
I'm not sure. But it can happen, and there's always two levels of those sort of things. One is the automated level, where you say, if this and this happens, I'm going to effectively say I'm out of here. And remember, these systems cascade onto existing base levels, so there really shouldn't be a safety issue switching them off. You lose optimization, you don't lose safety. So it might be that you have interlocks and things like that that will switch the system off. Or something I prefer actually is to count on the operators. The more you count on operators, the better job they do. So if you say to them, look, I'm giving you this thing, and generally the operators like the APCs, but you need to watch this and this and this, and if this happens, you can take control, then I think you are treating the people who are running your multi-billion rand plant as adults and giving them responsibilities. And I think that generally works well. You can be very sophisticated with the interlocks. You can do lots of clever stuff, but there's a cost element to that.
yes. Yeah, I think measurement seems to be quite the topic here. There's another question about how you handle, is it possible to safely handle instrument failures with MPC controllers? Do these have to be built into the controller initially?
This is another field I'm extraordinarily interested in, and I've published a paper with Professor Bauer, who was at the University of Pretoria, where we looked at sensor validation. And we did this even before the Boeing 737 MAX issue, which was effectively exactly that issue. And yes, you have to validate the instruments that could cause you issues. And it's very tricky because it inevitably involves setting up limits and rates of change, and that's not in my opinion not currently a great science in how to do it.
Yeah.
But yes, you do have to do it, particularly with analyzers and so on, which you know can drift and give problems.
Yes. Yes, I think we have time for more questions. Here's an interesting one. Kevin, in your experience, have you had equal success implementing MPC technology with rigorous models as much as you have with empirical models, given that plant engineers tend to be difficult fiddling with their processes live?
In 25 years of doing this, I've not done one project where all the models were rigorous. So where we might use rigorous models is where it's a fairly simple calculation. Level in a tank is a good example. So if you know the flow out, if you know how there's a change in the flow out of a tank, and you know the size of the tank and where the level tappings are, you can calculate the change in level. Density is another one where you can often do the calculation. But apart from that, we really have found that the empirical approach is better. We trust our models, we can interrogate them, everybody can review them, and they're developed in a time span that is reasonable for these projects. I mean, otherwise you're looking at master's and PhD level stuff to develop a model, and that takes, the best masters you're going to get done is in a year. We don't have a year to do the project, so I'm maybe overstressing the case. There has been some work done in very big distillation columns where step testing is difficult. So if you are interested in this field, you can look for some work by a guy called Jose Ferrer, but that's very specialized, I would say.
Okay, and then a question here about noisy measurements. Does MPC work on processes with noisy measurements?
Yes, fortunately it does. I don't know if you remember, there was one little picture I put up where the trend looked sort of was moving around. There was a blue trend and a red trend. That would be because of noise. But the way we derive the models using these FIRs, FIR is a filter, so we do derive models despite noise. Obviously, the more noise, the more testing you need to get the models. If the signal is too noisy, then you have a problem, and you may need to go back to the signal and maybe do some filtering on the signal in the DCS.
Okay, I think we have time for one last question here. When questioning a control room operator why he turned the controller off, the common response usually is, I didn't know or trust what the controller was doing. Have any easy to understand visuals been worked into SCADA pages to reassure operators of the action the controller is going to take?
Okay, that's a great question. I'm going to just go back to one picture here, if you don't mind, because that picture, that is a simulation, and we have colleagues who are very clear about how careful you must be about simulations. But that picture is on a television wall on the control room in Mount Isa, because it shows what's going to happen in the future, or at least what we think is going to happen in the future. And that, in my mind, trends like that are what is key for a human to understand what's happening with the process. So this trend can be formatted how you want. You don't have to put in all the plots, and you probably don't want it bigger. I think we can do 6x4 or something on one page. The 24 plots are plenty. So yes, I think there are tools, and if used by sensible operators, I think they lead to interesting discussions as well when you're commissioning, because the operator can see what the system is doing. It's quite transparent.
Yeah, thank you, Kevin. I think we've run out of time for questions. Thank you so much for your very insightful presentation. If anybody, if you have any more questions or anything you'd like to ask Kevin, you're welcome to send him an email or contact any of us. We'd be happy to answer any questions you have. Over to you, Valalam. I think you want to make some closing remarks.
Thank you very much, Merinda, and thanks, Kevin. What a great presentation. So thanks for the preparation and sharing that information with us. Guys, if we haven't answered your questions yet, you can carry on typing, and Kevin, Merinda will get back to you in writing. So this event is recorded, as you can see, and so even if tonight you're revisiting or if you share it with a colleague and he has some questions, that question will still come through to us, because it really it lives on, and we will get the questions and we will get back to you with those answers. So please engage on this event, or if you revisit it a week from now and you have another question, just type it in and it will get through to us, and we will basically be able to answer you on that. So, and thanks for all the engagement. I think we were peaking somewhere over the 90. I never knew there were so many people in that's so interested in advanced process control, or maybe they just wanted to hear Kevin. He was a lecturer in previous life, so a lot of his ex-students probably want to also listen to him again. So that was a great one. So I think the next theme is there is many more of these events happening. So we're having another 2 advanced process control events as well coming up. So please follow the links again. So we'll send you a thank you note after that, and there's more links so you can register for some of the others. So we will at some stage still have AspenTech presenters also talk about the vision, the future, the this combination of bringing advanced process control into the tool of advanced process control. And so we'd show you and share some of that technologies. We normally would do training on APC, the MC3, and that in our offices. Obviously now with COVID-19 that's not possible, but we're carrying on with e-learning. So there is free e-learning to AspenTech clients up to the end of June. It might be extended again. And also we're doing virtual training. So last week we did virtual training for an audience. Next week there is again. So training carries on. It's just now in a virtual space with a lead instructor. And then I think the last one is if you believe that anything that Kevin or Merinda shared with you is valuable and you would like to engage with either of them or one of our other advanced process control consultant or engineers, send us a text again, either reply on one of the emails, confirmation emails, or in here in the Q&A area, and just say, listen, I would like to speak to an advanced process control business consultant, and they will get back to you. With that, I would like to end the event and thank you for the participation. We had tremendous engagement in this event. I think Kevin and Merinda did great. Thanks for taking the time, guys. See you on a future webinar event every Wednesday at 2 o'clock for the next 9 weeks. We'll be here. Thanks, everybody.